Well, nitrogen is made up of, it's a sigma state, but it's a sigma state from the confluence of pi bonds. Okay. So now if we look at this symmetry operation here, okay, when we look at, I'm going to define this one as the pi x, and this one we'll define as the pi y. We notice that in this case, in this reference frame here, the pi x has this negative symmetry operation. It's changing signs. Okay? Whereas the pi y is this positive symmetry operation. It's not changing signs. Okay? So if we look at nitrogen and how we get to that, and remembering that we have a whole mess of this stuff, okay, we're going to have, the way this is going to work, when I break apart my 1 pi x u, both of those are negative, okay? So a negative times a negative makes a positive. Now what about the 1 pi y? Well, we define both of those as positive terms. And then, of course, the 2 sigma electrons are also both positive terms. So a negative times a negative gives me a positive, and there's positive symmetry operations the whole way through. So indeed, N2, 1 sigma g plus is a closed shell homonuclear diatom. What about this O2 example? Let's go through this O2 example, and I'm going to go through this in full detail. And you can see what I've got here is a empty MO diagram. And I'm terrible at drawing these things by hand, but I think there's some real value into you either, making some of these electronically or drawing them out by hand and populating them up. I think there's some real value to going through and doing this, okay? So let's go through and do this full O2 example, all right? So we know that O2 has, I had to count for a second, 12 total electrons. But if we look at its valence shell, so 12 electrons, 6 and 6 from each, we're really only worried about, why did I just draw a blank there? Oh yes, because I'm looking at one diagram and I'm looking at this diagram. Apologies. Okay, so yes, 6 valence electrons, so 12 that we need to deal with. Okay, so let's populate them up. So we know that we've got 2 from each 2s oxygen, right? So that's going to go 1, 2, 3, 4. So we filled up that shell. So now I've got 8 left to distribute. So we'll go 1, 2, and then this is how we're going to fill this out. 3, 4, 5, 6, 7, 8. Okay, and you notice that I made a triplet state out of this because remember, one of Hund's rules, if 2 different degenerate orbitals exist, and that's what we have here with the 1 pi xg and the 1 pi yg. They're different, but degenerate. If 2 different degenerate orbitals exist, the lowest energy configuration is achieved with the triplet state. Okay, beautiful. So now, let's go and get the term symbols. And so as you might guess here, we know that this 1 sigma g and 1 pi u, it's all going to shake out to 0, right? Okay. Well, the 2 sigma g, that's going to be 0, okay? Well, remember, we did this example for nitrogen, and this is all going to work out to be 0, right? Because if I call the 1 pi x -1, I've got a -1 and a -1. But then on the other side, I've got a +1 and a +1. So that all cancels out to 0. So now the only thing I'm really going to consider is my 2 electron system right here, these 2 unpaired electrons. And this one gives me a -1 on this side, and this one gives me a +1 on this side. So -1 and +1 makes it a sigma state. Okay? I can also see that it's a triplet. Hopefully you recognize now that 2 upspin electrons like that is a triplet. So I'm automatically going to put 3 sigma. Okay? We can see that it's a G times a G to give me a G. And then also, what about my symmetry operation? Okay, well, I've got 1 electron in the X, which is a negative. I've got 1 electron in the Y, which is a positive. And a negative times a positive gives me a negative. So the O2 ground state molecular term symbol is the triplet sigma G minus. Okay, folks, it's been about 30 minutes. And what I want to do, I'm going to describe one more term symbol, and then I'm going to